Thank you very much. My name's Evan Mishula. I'm a graduate student at the City University of New York Graduate Center in Criminal Justice, and I am a 2014-15 GC Digital Fellow. So that's how, those are the people I need to thank. All right, so my talk is Org Mode as a tool for reproducible research. Reproducible research is a pretty simple concept. It's the idea that scientific claims, or especially computational claims, should be published with their data and with the software code used to analyze them. Claerbout had a statement in one of his papers that has been repeated often. You'll see it in a lot of the defining literature about reproducible research. It was that an article about computational result is advertising, not scholarship. The actual scholarship is the full software environment, code and data that produced the result. So what we see in scientific journals, high impact journals many times, is we see advertising. I did this, my algorithm does this, it has this, but if you actually try to reproduce it, you can't get the code, you can't get the data, it doesn't run, it doesn't link, and I have some statistics that we'll go through on this. So the person who made Claerbout's statement most famous was probably Donahoe, and their famous statement about this, which is in the Org Mode paper in the Journal of Statistical Software, is when we publish articles containing figures which were generated by the computer, we also publish the complete software environment which generates those figures. So we're going to talk about the scope of the problem. We're going to go over some definitions, current practice, tools, particularly Org Mode and Babel. And at the end, I'm going to ask your indulgence because I'm going to say a few words about what I think we need to do to change this situation. And Emacs users tend to be people who do things rather than make policy. So I'm speaking from the perspective of somebody who doesn't have a huge budget and doesn't have a fancy title. And what can we do by sheer intellectual force to change the situation? So is reproducibility a problem? I put the hashtag in there because there's a hashtag actually where people tweet about reproducibility. So in 2012, a team from Amgen, this is no small fly-by-night company, tried to reproduce important results in preclinical targets for cancer. 47 out of 53 major, well-cited results were not reproducible, and they published this result in Nature. So, not 47 out of 53 were reproduced, 6 out of 53 were reproduced in cancer. And I think that, for me in criminal justice, I always know that our statistical treatments of things are terrible. And, but I always think, well, somewhere out there, somebody is doing a much better job. And before I started to look at this, I would have thought medical research had to be doing a much better job. But that's not, when you look hard at this, you find that the situation is pretty terrible across the board. In psychology, which has a reputation for lack of reproducibility, there was a 2006 study that of 249 data sets from the American Psychological Association with empirical results, 73% of the contacted authors did not respond to requests for data within 6 months. So we have data, what happened to that data, why we're not sharing that data, not altogether clear. This is from Ioannidis. He's now a professor at Stanford in the medical school and in the Department of Statistics. And he was asked, they did a Psychological Perspectives did a review of all the empirical research in the cases where where replication had occurred, how often it occurs, and what the likely results would be for when it doesn't occur. So this is a 2x3, right? So the discovery result, correct, could either be correct or wrong, and the replication can either have 3 outcomes. We can either get the replication correct, we can get it wrong, or most often, it's just not done. It's just not done. So when both are correct, there's a replication of an original result. It's much less than 1% of the time. If the result is correct and and the replication actually says the result is incorrect, that's way less than 1%. And an unconfirmed genuine discovery happens about 43% of the time. Most of the time, the result is wrong. The perpetuated fallacy happens with a confirmation of a wrong result about 2% of the time, and an unchallenged fallacy happens 53% of the time. And I put the title up because I thought it was so good. Why science is not, because one of the things we think about the scientific method is even if things are bad, we'll eventually get to the right answer. But here you're getting to the right answer very, very slowly. Probably the most famous case of irreproducible research happened in economics. Or maybe we should think about this in a better way. We discovered how bad the state of economic research was by somebody being honest enough to let their data go to a graduate student. So Reinhart and Rogoff, 2 economists at Harvard, wrote a very influential technical paper called Growth in the Time of Debt, which was published by the National Bureau of Economic Research. It said high debt to GDP and low GDP growth are associated. So in their academic work, they were very careful. They did not say that high debt to GDP caused low growth. They said they were associated together. In their editorials, in their interviews, they were much less circumspect about the results of the paper. They made their calculations in Excel. And the paper had a substantial popular impact on austerity politics. In politics, academic studies are used as weapons. They're used as weapons to get votes, to shame people on the other side, and this was used to by deficit hawks to enforce austerity on a number of countries. A graduate student at the University of Massachusetts at Amherst wanted to replicate the paper for a course. He requested the supplemental materials, and he found the error in coding. Tim Herndon, who was the graduate student, Ash and Pollan published a rebuttal to the paper. And Phil Stark is a professor of statistics at Berkeley. He said, relying on Excel for important calculations is like driving drunk. No matter how carefully you do it, a wreck is likely.
That does not have enough favorites.
Yeah, no, it does not. It does not. So, what's the situation in computer science? I would say that it is shockingly not much better. So Christian Kohlberg and his team at the University of Arizona looked at papers in 8 conferences and 5 journals in 2012. This is not from the Stone Age. They contacted, they had elaborate rules for who they were going to contact. They contacted all of the authors eligible. When I say here that they reproduced, I'm not talking about they got the same results. I'm talking about they got the program to run. They couldn't get most of these programs that they received from colleagues who had published the results in major ACM journals to run. There were compile errors. There were linking errors. There were seg faults. These are the result here is the number of programs that ran to completion in computer science. So let's talk about the history of reproducible research. So the mathematical proof, while it's been around for a long time, it has changed. And there have been controversies about what constituted a proof that have gotten worked out over time. So Pythagoras definitely had the idea of a proof. Euclid of Alexandria was the first that we know of to use axioms in definition. Eudoxus was the first one to make theorems. William of Ockham, Occam's razor, which most of you have probably heard that, favored logical systems with the fewest number of axioms and proofs with the fewest number of steps. The 19th century was the golden age of, in many ways, of mathematics and also of mathematical proof. Fourier had expansion of arbitrary functions into trigonometric series. Galois and Cauchy outlined the group theory and the beginnings of abstract algebra. Riemann, differential geometry and complex variable theory. Cauchy, partial differential equations. Jacobi, Kummer, and Abel, number theory. Lagrange and Cauchy, calculus of variations. Classical mechanics, the implicit function theorem. And Weierstrass, real and complex analysis with numerous examples and counterexamples and rigorous proofs. But to think that it was just one progressive line in the 19th century would be a mistake. There were people who opposed replication in the same way that medieval mathematicians hid their proofs. Gauss had what can only, although Gauss was very rigorous, he was not happy with the proof, his PhD thesis was on the fundamental theorem of algebra. He was not happy with the prior work and thought that the proofs were too weak. But his style of proof was not to show where the insight actually came from. And I don't know. So Bourbaki was a movement in France to put mathematics on a rigorous foundation, and it was a group of French mathematicians writing under the name of Nicolas Bourbaki, but it was not actually one person. But the Bourbaki program specifically rejected intuition of any kind being shown in a proof. And also, and in this way it was sort of like Euclid. Like if you read Euclid's Elements, you don't get a strong feeling about what's important and what's not, and why something would be considered a major result and what's not. And at least in some of the work that I've read, people thought at the end of the day the Bourbaki program probably set French mathematics back rather than moved it. Good. I'm ready to.
I disagree completely.
Okay. Well.
But anyhow, that's not pertinent to the talk.
Yeah. Okay. Well, I would love to be educated later. So Gauss said that no self-respecting architect leaves the scaffolding in place after completion of the building. And, but it's very hard to climb to the top of a castle without a staircase. And sometimes I felt, when I read his stuff, I felt like there was no staircase for us to follow. I wanted to put this in, this doesn't go exactly, but one of the, there were a lot of, was a lot of work on the fundamental, logical foundations of mathematics in the 20th century. And a lot of people obviously used proofs by contradiction to come to conclusions about set theory, about real analysis. Everett Bishop, who was a mathematician at Berkeley, got very nervous about all of this and thought that that reliance on the proofs by contradiction, while expedient, could lead us in false directions. And so he invented constructive analysis. And in the process, he also came up with a good definition of a proof, or a good working man's definition of a proof, which is that a proof is any completely convincing argument. Okay, so that's the evolution sort of mathematical proof. Let's look at experimental proof. There have been some major steps forward in that as well. So Robert Grosseteste, who was also the Bishop of Lincoln, was the first one who looked at Aristotle's work in the West in the Middle Ages and reasoned from the universal to the particular, and thought that that we should be making predictions about what should happen. And his famous work was Posterior Analytics. Bacon was a student of his, and he was the one who invented observation, hypothesis, and the need for independent verification, which is still the heart of the reproducibility issues that we're in today. Galileo manufactured multiple copies of his telescopes, again, so that we were sure that we were getting true results. Pasteur added the materials and methods section, which you find in any scientific article. So the modern leaders of reproducibility. So I think that we owe a tremendous debt to Knuth, who invented the idea of literate programming and gave us LaTeX. Obviously, I don't think any of us would be here if we weren't huge fans of the Free Software Foundation and Richard Stallman. The idea that one of those freedoms is the freedom to learn, to examine the code. The idea that that most results in science are the result of calculations that nobody has the right to examine still confounds me. Lessig, Abelson, and Eldred created the Creative Commons, which allowed for the free licensing of non-code, which figures and which are part of the digital objects that make up science. Linus Torvalds, aside from giving us Linux, gave us Git, which sometimes I don't know if that's a blessing or a curse, but it is no doubt the software that facilitates the greatest collaboration project in the history of software. I never tire of telling people that the Linux kernel changes 7 times an hour, 24 hours a day, 365 days a year. There's just no other software project that can match that rate of change. 2 other people who have made major contribution, John Ioannidis, so the largest open access journal, or the most widely read open access journal in the world, is the PLOS, the Public Library of Science. It's medical journals. He published a paper called Most Published Research is False. It is the single most downloaded paper in PLOS. And what he says is between 1996 and 2011, there were roughly 25 million scientific papers. And there are 15 million people doing research. And most of that research, most of what is called a scientific discovery, is in fact false. And that approximately 85% of research assets are wasted. Now, I'm in criminal justice, okay? We know how to waste money. We know how to waste money with the best of them. We have marijuana laws. I mean, you know, you just can't throw money down a toilet any faster than that. But the idea that we're wasting 85% of the 23 billion that we spend on the NIH or the 6 billion that we spend at NSF is pretty stunning. Victoria Stodden, who was at Columbia and now at the University of Illinois Urbana-Champaign, created a legal framework for reproducible scientific research. She's in addition to having a PhD in statistics, she's also a lawyer. And she founded 2 websites which help people to verify that their claims are reproducible. One is Research Compendia for articles that are already published, and runmycode.org, which basically hosts virtual machines and websites associated with scientific papers. And the article at the bottom is the legal framework. So the next couple of slides, I just basically stole from Victoria Stodden's talk at Berkeley and Ben Marwick's talk, which is up on our pubs. And I just wanted to situate org mode within the general tool set of reproducible research. So there are dissemination platforms. That's Victoria's term. And so they include Research Compendia, which is for articles that are already published, machine learning open source software for all machine learning software. I didn't know about that. I figured somebody else might find that useful. The Data Hub hosts data sets. The Open Science Framework is a website that starts with planning to publishing. One of the biggest biases and one of the reasons that so much science is wrong is because of publication bias. So publication bias is we do 10 studies and none of them have significant results, but the 11th study gives us a significant result, and that's the one my advisor says we can publish. But all the other 10, nobody ever hears about. So there's a tremendous duplication and waste because we don't do that. So registration of data sets is something that Iodanis and others have called for so that we know what studies are actually being done. Madagascar is a multidimensional analysis platform. NanoHub is a simulation platform for nanotechnology. RunMyCode, Code and Data. Research environments, and this has been an area of rapid progress in the last couple of years. VizTrails has Python libraries and LaTeX. The Kepler project are wrappers in Java for R and C. Galaxy is biomedical data analysis. GenePattern is a big gene analysis framework sponsored by Penn State and Johns Hopkins. Sumatra is an electronic notebook for simulations, which have their own set of particular issues and parameter tuning. Taverna is a workflow management system that integrates with R. And CDE is portable Linux apps with data and dependencies. This is done by the University of Eindhoven and seems to be very similar to Docker, which I didn't put on that list, but maybe should be. And then org mode itself falls into what would be the embedded publishing or literate programming frameworks. So Jupyter is a new project led by Fernando Perez and Brian Granger, who were the driving force behind IPython. And it is to make interactive computing environments for a variety of languages. So IPython has been sort of one of the most successful REPLs to date, and so they're expanding their work. There's another site called Verifiable Computational Research. Donahoe and someone else, I forget, they're at Stanford. It's basically a MATLAB plugin, and that's proprietary, and we all know that proprietary is bad. So, Share at the University of Eindhoven, and then two others that are specific to R, but I think SWeave has to get particular notice because it was one of the first practical systems for integrating text and figures in a reproducible way. And it's now a few years old. Knitter is sort of the replacement package in R that has gotten, that's gotten a lot of, that's seen a lot of people migrate from SWeave to R. I, of course, migrated, I think, from SWeave more to org mode, and I think org mode has some advantages that over the rest of these tools and for my workflow, because although I principally use R, I don't exclusively use R, and so I love the idea of being able to work in any language that I need to, and basically because it's always much better to steal code than to write code. Tends to be much faster. I want to be able to put other good code that I find or that somebody gives me to good use. So this part of the talk I've ripped off from John Kitchen, who's a professor at, and I'm sure he'll watch this at some point, who's a professor at Carnegie Mellon in chemical engineering. He gave a talk at the Scientific Python conference in 2013 on Emacs, org mode, and Python for reproducible research. It's a very good talk, and I recommend that you see it. And the way that he structured the talk was he said that publishing or an embedded publishing system should solve three problems for him. One, it should document his computational workflow. Two, it should integrate text and math and code. And three, when he goes back through his figures and he takes a look at the figures he's produced, oftentimes he wants to know, number one, what is it that produced that figure? And number two, maybe I want to modify that figure. If you're involved in an active research program and learning, one of the quotes I didn't put up that I love is from Einstein. And Einstein, or one of the things that Einstein is reputed to have said, is that, if we knew what we were doing, we wouldn't call it research, right? And so there's often times in research where your ideas about the problem are changing very quickly. And so sometimes the solutions that you have are moving quickly. And so it's oftentimes that we produce figures, or figures get disseminated to bosses or department people or whatever, and we're just not sure when they bring them back to us, what version was that from? Where is that from? How did I produce that? And so that was the third problem that John mentioned. So it's a little, in this crowd, this is gonna be repetitive, but maybe somebody on the internet will find this and maybe they'll have a little bit of stuff. So excuse me for a second. So Emacs is written in a full programming language. It understands LaTeX and Markdown and language modes, R, Python, C, C++, and Java, etc. It can interact with the OS. It can dispatch processes. It can execute code. It can read the standard output from that code, and it can read the error. And so any editor, even one that is not Emacs, that could do these things could support this kind of flow. But if an editor can't interact with the operating system in this way, then it's beyond my ability to see how it could ever be part of this reproducible research flow. So org mode is obviously, well, not obviously, it is a note-taking system. It manages to-do lists, and it also can differentiate between text, code, and data. It can execute code and manage the results of that code being written into the same buffer. It enables links to files and URLs, and importantly, and this wasn't in John's talk, it allows for an include statement, which allows us to manage large projects by breaking them down into smaller functions. So all of us reuse functions all the time, but when we're talking about large documents like dissertations, like technical books, like large articles or compendium of research, the ability to break parts of the text off into their own file is invaluable for managing the project. And it exports to all of the, or at least all of the ways that scientific information is communicated that I know of. So it can create LaTeX files, it can create PDFs, it can create HTML code, it can create this JavaScript that drives this this reveal.js presentation. Okay, so we have to initialize the languages. This is in the nitty-gritty of org mode. And this is what I use to do it. So we load the languages. Emacs Lisp is loaded, Haskell is loaded, Org is loaded, Perl is loaded, Python, R, Ruby, the shell, SQLite. I set because it's running code on my computer, the default for security is to ask me every time I want to run a piece of code if I want to run that code. So I set the confirm Babel evaluate to nil so that it doesn't ask me that. And then I set the default export to code. This is one slide that did not work, all right? So anyway, there's supposed to be a bunch of files there. I don't know why. I'll fix it. It'll be in GitHub the right way. This is how it would look if I just exported only the code. But what we really care about is how it'll look in org mode. And so the name of the function is sort files. There'll be a boundary header, a begin source and an end source. This tells it what language we're talking about. Here it's SH for the shell. These are key value pairs or dictionaries in Python. So this is results. So this says what kind of result do I want to see? Output means that it will print all of the results that would have printed in the shell. And when I export this, when I invoke the export engine on it, I want to see it export the code, all right? And then this is just a shell command, list all the files in the directory, and then sort them. So I can do this also in Python. It worked in Python. So in Python, I would import the OS. I invoke the list directory, then sort the files, and then for F in files, which is now the list of files, printf, and it prints there. So this is an equation, or three equations. This is the raw LaTeX. So we see begin equation, end equation, if you've worked with this. This slash paren is an org mode designation that LaTeX is to follow. Again, here's standard LaTeX. And again, here this slash paren and slash paren indicating. So this is raw LaTeX. And we can hit, and so we can generate LaTeX, what are called LaTeX fragments in org. And now we can see the compiled LaTeX. So the compiled LaTeX looks like it would look in a PDF. So we've solved the first problem, and we've solved the second problem that John posed. So create a graph. This is a 3D scatter plot. And so this is our code. We've got sequences, we've got data frames. We require scatterplot 3D, which is in our library. We create the graph, and we orient it. We create it. We can link back to it. We've embedded this in the presentation. And this is how the graph function looks actually in the org mode buffer. So again, we have the name, the header, which is quality 100%, which in this case doesn't do anything, and that actually only does something in JPEG. But again, we have R is the language. We are generating a file here. This is the name of the file that we're generating. The results that we're getting out are graphics. We want to export both in this case, both the code and the figure. The code that you saw before. And so, my final thoughts on how do we make it better. So, those of us that are doing research, we shouldn't submit or cite journals that don't make code and data available. Frankly, if the result is probably wrong, there's no reason to cite it. Grad students, assistant professors, we're often, postdocs, we're often asked to review articles. I will not review an article unless the code and data are provided. I am not going to sit here and say, wow, what an amazing result, if I can't run it myself and believe that it actually occurred. Within your institutions, promote free and open source software. I think that's the easiest thing to do. We're finding at the City University of New York, and maybe I'm an optimist, that we have a lot of people who are listening to us. There are plenty of tenured faculty who want to continue to click their way through their next 10 publications, but there are many, many graduate students who know that they've got to do better than that, and there are many administrators who see the tens of millions of dollars going out the door to proprietary software as money that they can repurpose. And then don't work for an advisor that won't learn source control. So, there's more I can show you if you're interested. If not, you're free. And I'll take any questions anyone has.
So, in R to
Yeah.
can you cache the intermediate objects?
Yes, yes. So, okay. So like, let's get real here. All right, let's get out of the presentation BS. Okay, so tell me if we can see this or if I have to make stuff bigger.
Bigger.
Zoom it a smidge.
Okay. All right, let's see. Give me 1 second, then I will zoom. Okay. So this is my proposal. I mean, so what I have, so Randy just asked a really good question, which was, can I store intermediate results? And so what I do here is I have what's called a session. And so my session is called New York City. And in that so I can run part of my analysis, go into the session, and then all of my data cleaning has happened. And so I clean the data the same way every time. And you know, one of the biggest downfalls that people do is they clean data by hand, or they have handwritten notes about how to clean data. You cannot do that if you're analyzing data every day. You will do it wrong someday, or maybe not even wrong, just differently. And nobody is ever going to ask you about how you clean the data while you're cleaning it. They're going to ask you 8 months later. So, yeah. So anyway, you can save those intermediate objects. Any other questions? Yeah, Ann?
So are there some examples of, people who are providing this? Like, can I go out and review some things already?
So, yeah, I mean, there are, so obviously Run My Code has all computer science papers that are available and will run. The Journal of Statistical Software, which is where the org mode stuff was published and where there were, a variety of Hadley Wickham's publications were made in, always provides a repository with every publication that allows you to fully replicate the paper. And so, the higher impact journals all have policies that say they do it, but you don't find, or study after study has not found those repositories to be complete. But the Journal of Statistical Software, I've never had a problem replicating what they've done. Yes?
So this is a comment on the question about this, right? I don't know if the Journal of Statistical Software is special. I mean, my field is astrophysics, and I'll tell you that in addition to the things that you're saying about what can you do to make the world better, the real problem is that there's laziness in review, right? I mean, you can say, oh, I'm not gonna review a paper unless you give me the code. Fuck you, right? Like, no one cares about you, right? They'll just go to somebody who matters a lot more than you. Who's not gonna sit there and be like, I wanna see the fucking code or whatever. They're just gonna be like, oh, looks good, sounds reasonable, the names on the paper, take shots, and it's out. Right?
No, but you know what? Well, at least in my field, the game with that, with those guys who don't read the paper, it's all who do you cite, right? So that's the way you want to get into a better journal, right? Cite me. You didn't cite me. Review and resubmit.
Let me rephrase, right? It's that I have done this, for example, right? I have said I want to see the code, right? And they'll be like, no. spirit still of being proprietary about your craft, because we haven't yet gotten, at least in physics, to the point where there's a culture that if you are holding on to your code and being proprietary about it, you're not actually doing science. We're not there, right? But then they just go to another reviewer because who the fuck am I, right? They'll be like, they give me the finger, they go to another reviewer, and they publish it anyway. And because
And those results are probably wrong.
they may or may not be wrong. It's not the point. The point is that even if all the things that you said that we should do, we do, there has to be another transition which is cultural, and I don't see happening anytime soon because there's a lot of entrenchment.
There is. I'm not gonna. Your comment is born of hard experience, and I'm sure that that's true. I just think that, maybe not within physics, but certainly within medicine now, there are enough people starting to clamor. And so one of the things I didn't put in the presentation that's really funny is, right, so Amgen basically threw down at Harvard and MIT and said your preclinical work stinks and we want your data and all this stuff. And they were like, we need to have this because that's where they're investing money. They're much less willing to share their clinical data, right? Because they don't want, because they know that if people get a hold of that clinical data, they'll use it to cut drugs off later on in the stage. Oh, somebody else has already seen this bad side effect. Somebody else has already seen, drug interaction. So, I mean, there's a lot of work, there's a big lift here to do. It's not like we're gonna solve this problem instantly.
Legal barriers in clinical data.
Well, I mean, they can anonymize the clinical data. The legal barriers are more about sharing code, because code is actually, unless your university lets you release it under GPL, right? Your code is actually owned by the university, and there are copyright issues around that. And code by default is copyrighted. So, I mean, there's legal stuff. I've chosen to ignore that part of it and just concentrate on, like, if we're doing science or software or whatever we want to call it, and how do we use the tools so that we're sure we're doing the very best we can not to kid ourselves. And the other thing is, like, in my field, there are journals, many journals, that only report significant results, right? We've got volumes of significant results. I mean, obviously that's got to be wrong. And so, we're gonna have to recalibrate our expectations that, in fact, most of science is about failure, and that most things don't work. And if we do find effects, we're going to find a lot of smaller effects. And so we're going to need bigger studies and more collaboration. And I just think that the more you know about the best tools in the industry to do that, the better prepared you'll be personally to meet that future.
So in some scenario, like, the data itself is proprietary, right? For example, if Facebook or Google publish a paper about their user behaviors, they have all the data sets, but they say first it's proprietary, we don't want to share with you. The second, we have privacy problems.
Mm-hmm.
How do you respond to that?
Well, I mean, there are some data sets you're never going to get at, right? So, I mean, there's classified physics research and all that. I guess the question is, what am I going to build on that? So if somebody from Facebook has a study with N equals 683,000, which was the last Facebook study about how people react to negative things in their Facebook feed, and they want to publish that, that's great. But, like, if nobody's ever going to give me that data or any data like that, like, what am I going to do with it? you know, but there are always gonna be there are always gonna be, things where it's impossible to share, but at least let's disclose that up front. And, you know, and then we can have a journal of irreproducible results, but, you know, and, you know, I'm sure some reporter will report on it, but I don't know. Yes, go ahead.
Probably a bit futuristic, but I wonder if anyone, you know, thinking of things like, let's say, going with, say, funding agencies, saying, okay, you know, we will require, you know, as a condition of the grant to get the data out, or anyone attempted that.
Absolutely. Like, let's understand that it's already there. Every National Endowment for the Humanities grant requires a data management plan. The NSF requires a data management plan. The journals require you to share. The problem is not that we don't have requirements to share. The problem is that nobody follows them.
The NSF doesn't enforce that at all.
Yeah.
Well, but then my question is, that the authorizations are, what are people doing to try to say that, you know, if you have it on.
So, I mean, it has become a small industry of postdocs working for Victoria Stodden to like go to a field, request data, get non-responses, and then embarrass people. Like that's like Kohlberg, the one I mentioned about computer science in 2012, that's what he did. So as soon as people heard that he was actually going to publish, how many of them said no? Like there was a firestorm. It's embarrassing. It's embarrassing for professional scientists, professional computer scientists, to submit code for replication that doesn't run. I mean, like, all right, yeah.
There seems to be a very kind of modern perception that the data is free. You know, like if you did a scientific study in the 1800s and you needed 20 cadavers, you made the report, you did your scientific results, you reported your results, but you didn't have to provide the bodies to the next guy who wanted to reproduce it. He had to bear the cost and the mechanism and the environment to go get bodies and do the scientific and reproduce it. If a medical group goes and does a study with 2,000 doctors around the world, collects that data, that costs them a lot of real money. And to take that data and just hand it out for free, even if it's valuable to reproduce the study they answered, that data is valuable in tons of other ways. And everyone else will take that data and mine the hell out of it and make a lot of money off of something you just spent millions of dollars on.
Well, but there are no, you said money
Shouldn't-
publicly funded.
Let me just finish under, shouldn't the responsibility be not to necessarily provide the data, to provide the methodology using scientific method in which you can reproduce the study? And if you want to go get your 2,000 doctors and collect your data, not with my code, not with my data, but I'll tell you exactly how I did it because I want it to be reproducible, it's up to you to write the code. Why do I have to give you my code?
Well, okay, so,
I mean, maybe you code like
So-
me and I don't.
oh, okay, well, maybe I do. I respectfully disagree with that,
Well, I don't
because.
even know if I believe it. I just-
Oh, okay. Well, I know I don't, because there are a lot of people that can describe their coding, and that doesn't match what is actually done. And so if I'm going to believe something, I want to be able to see it. And most of this, most of what we're talking about is publicly funded research. So we're talking about money. Most scientists didn't raise $2 million to go interview 2,000 doctors. They had an application to the NIH and they got an R01 grant. Okay, so that money came out of public coffers that they were entrusted to do their science.
Yeah, I understand that. I mean, if a taxpayer pays, we have a right to the data, no argument.
Yeah, okay.
If you don't, that's a problem.
All right, but we should agree. I agree, I just, from my world, it's very different.
Yeah.
So, it seems to me that data seems to be the biggest barrier of entry to actually do good things.
Yeah.
You know, try, get a good idea for the stock market, this gentleman was it, and try to start a company on it. The
Yeah,
barrier
good.
of buying Bloomberg data, you know, is tremendous.
Yeah, and so one of the things that's happened, because the replication problem has gotten so bad, is that there's actually a Journal of Science and Business, okay? And in the Journal of Science and Business, there was a recent paper that venture capital firms are hiring contract research outfits or organizations to replicate findings before they put serious money to work. Because it's worth it to those people if I'm gonna put $10 million into some biopharma company, I wanna know that this drug target has the properties that it's advertised.
I agree with that. I was thinking more, I just came back from Wolfram Conference 2 weeks ago. They have the computable document format, and this is antithetical to everything you're saying. It's a closed proprietary, for-profit company. They have this, but the idea is that they can take my data and my model, and they can wrap it up into something that looks like a PDF. And the idea is it's now protected. I can actually give it to you if you want to reproduce my results. You have a working model with all the description of what's going on, but I'm not giving you my work. I'm giving you my results, and I'm giving you a way to test anything you want. If you want to test if I'm right, you can write it, and now you can test against a working model that's running on your computer that I handed to you.
The question is whether reproducibility should become a prerequisite for calling it science. And at the end of the day, that seems to be the position you're at.
Yep.
I kind of agree with it, but it means that a lot of people are banking their tenure prospects on that one piece of software. It's not money for them. It's something else. It's a different currency. And they're scared shit. They don't want to let it go. They don't want to hand over this piece of code. They put it on paper on and let some scrub grad student write 50 papers in the same.
And tell them what a bad coder he was.
Yeah, right, which is what happened to Reinhardt. I mean, Reinhardt and Rogoff. I see you guys, don't worry, I'm getting to you. But you gotta give Reinhardt and Rogoff credit because they gave the Excel spreadsheets. They got embarrassed about it, but we're all gonna, in the process of writing scientific code, we are all gonna make mistakes. Maybe we won't make that mistake, we'll make another one. But that's what science is about. And so that's why I support, generally speaking, the openness of it. Now, I don't know which of you two were first, but I'm gonna give it to you and then I'll come back to you.
Yeah, I've dealt somewhat with labs, and the two problems. One is the management labs see giving away data as possibly a loss of an opportunity to monetize the data. And the second problem is, and some of you may laugh at this, but they don't know how to do torrent. And so much data could get out there if they're computer people in the lab who they know if they get FTP, they get cloud, but they don't get torrent. If they were to start doing torrent, that would propagate so much of the information out there.
Yeah, maybe that's another talk we can give. But yeah, I mean, we should make it as easy for them to do the right thing as possible. You got a question in the back, I'm sorry.
Yeah, my question was related to the example that is in the screen.
Yep,
So I see that you are the results become like org mode output, so you're generating more org mode.
I'm generating more org mode and then I wind up doing something indirectly with them. Yeah.
So why is like the
Okay.
So you generate more org mode and then this
Yeah, so the way this is structured, right? So these no export lines are all bury tons and tons of code and computation that I do. When you start to see things that are exported, that's actually where my text is. And so one thing I haven't figured out is how to get you see the equations actually stay the same, the one size and the text grows. But let's see if we can get something. So So, okay, so this is what I wanted to show you. So this is the no-web syntax, all right? So I have those results earlier, and then I can replace with those results and create a table. And so this is the, this less than, greater than. If you use, if anybody's used SWeave before, this is part of Knuth's no-web specification. And so it allows results from earlier calculations to be formatted and put into tables.
So the original R block generates the.
Generates the org code. Then the org code gets put in here into the table and formatted by LaTeX.
And the original one is not exported, and only the generated one is exported.
Yes,
Oh, okay.
Is that R specific, or can it work with
that can work with anything.
Python, NumPy?
Python, NumPy, any of it. So if I didn't get a chance really to put that as one of the examples, so give me I have to defend my proposal, so give me like 3 weeks, and I promise I will put that up as an example, because that took a while. The other thing that took a while, that I didn't get right away, that made my life so much easier, was the includes. Like, just to be able to manage big blocks of code and so initialize my session in one file, load all the data and be able to run that, and then I can play around. So, but definitely that no-web syntax is, it's in the org documentation, but it's just not obvious. Yeah.
I got another question about the flow. So it's did you ever eval all the code blocks, or you just go one by one and you just like?
No. So when you export, right? When you invoke the export engine, it evaluates all the code blocks sequentially.
Okay, sequential.
And then because I use the session, right? And so once it evaluates once, then it's already loaded the data in, it's already cleaned the data, so then I can do whatever I need to do for incremental progress on it.
Have you found any issues with that, like when the generation, the export takes a long time? Or?
So yeah, this is the sort of the constant battle when people are doing reproducible research. They're like, well, it takes a long time because I generate my figures every time. But ultimately, you're paying for. That's what you want to be paying for, because then your figures are never out of sync with your code. There is something which I do not use, but I read in the documentation, called no eval. You can set your code blocks to no evaluation, and then it will just generate the document. I don't use that, but if you ran into a big problem with processing speed, you could do that for small changes.
I got another one.
Okay, does anybody else have any questions? All right, thank you all so much for your time, and I want to